Hello, everyone, and welcome to a new edition of Cybersecurity Day, Week 3. Today's topic is binary exploitation. Who did practice binary exploitation during the week? If you did, raise your hand, please. Okay. Let's see how it's gonna go. I think everyone knows me right now, so I'm just gonna jump through this. So what do we have in the agenda today? First, why C is problematic, and is C really the problem here when you are talking about memory errors and so on? Also, we will do a deep dive into memory errors. What are they, and how do they look like in C? Then we will go through the execution of C. What exactly happens when we try to execute a function? How does our CPU exactly translate it into something it does understand? And then we will do our first stack smash, or basically we're going to do our first buffer overflow, and yeah, we ourselves going to segfault the code with our intention and not because we have buggy code. At the end of the first hour, we will do the first mitigation, which is the canaries, and they are mitigation of buffer overflows. They are meant to prevent people from achieving remote code execution or changing the execution flow during the runtime. In the next hour, we're going to do a little bit of shellcode. We will understand why we did even come across shellcode and why do we even write shellcode, and then we will do like how it's going to look like today. Is it still needed? Do we still use it today? Some restrictions, for example, we have a non-executable stack, and of course some workarounds, and then again a mitigation. Mitigation is basically a way to protect against a specific attack vector, if you don't know. Last but not least, a little bit of history. It's not going to be about the European history or like the world history. It's just going to be binary exploitation history, and then just an outlook about next week. Okay? So, own, pawn, or pawn. Does anyone know what is pawn? I already said this before, but does everyone here remember what does pawn mean? Does everyone? Okay. Leave the mic with you. What is pawn?
It's
Yes.
hello.
Yeah.
It's basically to have the control of a system.
Exactly. So pawn in a system, basically owning a system. And pawn, it represents, or it's like a shortcut of saying binary exploitation. It's not always related to binaries. You can pawn also a server. You can own also a website. It's not really related to binaries, but most of the time when we are talking about CTFs, we link it with binary exploitations. It's the hardest category out of all. This is not from me. This is the opinion of the majority. I mean, the majority of CTF players, of course. Because it requires a deep understanding of C, and the majority of people finds even Python hard, so nevertheless C. Of course, you also need assembly because you have to understand how your CPU is executing this to find bugs, and also how computers works, because it depends on the architecture, the system, the operating system, and also the binary and the libraries. It's also quickly evolving, so you might find a bug today and it will be patched, and then you can forget about it. So you will never see this bug ever again. Or maybe if someone wrote buggy code. The percentage of binary pawners is much less compared to web pawners. This means that it's a small niche. It requires a really good knowledge of the system. It requires also a lot of hard work, but hard work here pays off because it's in high demand if you know what you're doing, of course. You can also use it in the web, but from another perspective. Do you guys know how we can use pawn in the web? I mean binary exploitation in the web. Anyone? Please? Mike? That's good, but it's not really the point here. That's what I meant by another perspective, so don't really think about the web, like the web interface you see, but something else. Yeah?
Maybe on the server there's also just running some executable that takes some
Exactly.
user input.
Exactly. You can have another idea.
Another idea would be like through the runtime, through V8. That
Sorry?
maybe there, through V8, the interpreter engine from JavaScript, that maybe there's a mistake somewhere that we can go through that.
Amazing. So these are two famous examples of pawning a web from another perspective. The first one is basically the web serve. It's basically a binary. I think, did everyone here did web serve or not yet? So the majority understand that we have basically a binary running on a server that actually serves us something, or a website or whatever. This is also a binary, which means it can also have bugs, and it can also have buffer overflows. The other example was V8. Do you guys know what is V8? JavaScript engine. It's the engine in the browser that basically runs your JavaScript. And there is a specific category in binary exploitation called browser exploitation. And this is one of the hardest ones, but it feels different when you find a bug in the browser. So people finding bugs in a website, you found a bug in the browser. It's not the same. Sorry, but it's not the same. Yeah, so as I said, it's machine, architecture, and also libraries version depending. Do you guys remember why it is libraries version dependent? Anyone? Yeah, please.
If the library had some vulnerability that was fixed, and maybe in the new version it's fixed, but maybe the server's running the old library. Or
Do you have an example of a function which is in all the libraries but was bugged, for example, and right now it's fixed, or I don't know? No, I'm talking about just C libraries here. Easiest one, malloc. Malloc, just malloc. Malloc, through the years, had a lot of bugs, and you could exploit it in multiple ways. And even right now, there is always ways to do it. So malloc you're using, it basically has, I don't know, like 2,000 lines of code or something, if I remember correctly. It's huge. Of course, this is because malloc does a lot of optimization in the background. It doesn't give you directly the allocated memory. If you want to just allocate memory, you can use mmap. Mmap, yes. But malloc does a lot of stuff, especially when it's trying to free and give memory to you which was already freed and stuff like this. Yeah, sure.
So you said earlier about something about V8, which is the JavaScript engine that is run in the browser.
Yeah.
Is it, you said about exploiting it, or does it mean we are trying to exploit the browser itself or the website that is serving us the front end?
We are exploiting the browser itself, which means all the websites in this browsers are doomed.
Okay. And my second question is, for the web part, pawning the web, does it mean that we need to know the C language, for example, to be able to pawn the web, or do we need to know the specific programming language that was developed in?
For example, pawning the browser, most of the time it's you write JavaScript code that pawns the browser.
I'm talking about the server.
I mean, if you're talking about server, it also depends on the language of the server. If the server is written in C, your exploit should be targeting a C code, which is a normal binary. If it's written in C++, your code should be targeting a C++ binary. It's not related to the language of the website. Again, we are talking about a web server, not the website. Okay? Does it make sense?
So it's not the backend. It's you said a binary in the web server. I didn't get this part.
Look, web serve, it's basically any server that serves you something. This is a web serve. It can be defined in a lot of ways. You can, for example, have a Django web serve. This Django website will be written in Python. Of course, Python is not going to allow you to do a normal overflow. There is bugs. There is also binary exploitation that targets Python code. But what I mean, it's always depending on the language. So you can have a Django backend that could be exploited in not a standard way, which is like directly attacking the backend, but the server itself.
I see. And do we need to look about for those vulnerabilities ourselves, or do we need to search about people who found it and we try to relate it, like
It depends. I mean, it's not gonna like you're not gonna start today learning about binary exploitation and tomorrow you're gonna find the next critical bug in the browser. It's step by step. This is always it's like stairs. So you cannot jump to the second floor. You have to walk through slowly and just walk. Yeah.
thank you very much.
Okay. So issues with C. The first issue with C is this trust me, bro. So everyone writes his code and thinks, yeah, just trust me, my code doesn't have any bugs. And when there is a bug there, he just says, yeah, C is unsafe. Sorry, but you are the one who's writing unsafe code. It's not really related to C. C gives you control. If you cannot handle C, please don't write code in C. You can write it in Python, for example. Problems always arise. I mean, one of the first problems, I wouldn't say problems, but one of the things that make C exploitable is the architecture. So we have the architecture of John von Neumann. Do you guys know it? Okay. Can someone explain it? The microphone?
Yeah, okay. There are different parts of a computer, and he defines kind of principles for different tasks they have to do. Like I have heard about the model, but I don't know exactly. But I think he defines kind of a processing unit, some storing units, some memory access buses, and that stuff. But how it is very much in detail, that's all I know about it.
Okay. Does anyone have any other input? Thank you. Okay, so long story short, the John von Neumann architecture allows you to mix the control informations, the user data and the control data. They will be toggled together in one place, which is, for example, the stack. You can put literally everything in the stack. You can put instructions that could be executed. You can also put strings. All of this can be put in the stack. And if you think about this logically, if you are taking something from the user and you allow it to reach some other stuff which is meant for the computer to run, problems will arise. I mean, whether it's web, whether it's binaries, you never trust the user. The user inputs should not be sanitized. It should be rejected if it violates anything. And that's one of the reasons why we have also segmentation faults. The CPU doesn't try to run something that doesn't make sense. It will just say it's a violation of what I know, and yeah, this is a segmentation fault. Yeah. Also, do you guys know what is a metadata in C? Because C have this mixture between data and metadata in one place. This is the difference between learning practical C and learning the theoretical C. Metadata is basically the \0. It's the null terminator of your string. Why is this a metadata? It's because it is something predefined in the compiler, and the compiler already understands what does it mean. So if you have a string and you're terminating with the \0, it's not going to try to run what is afterward. It doesn't matter if you're putting \0 within the string or after the string. It's just going to reach it and stop. Okay? Also, one of the issues with C, which is the reason why we see like a lot of bugs today, is the initialization and the cleanup. Like, for example, free. You initialize something with malloc, you forgot to free it, or you double free it, which is one of the most famous examples of exploitation, double free. This is a really, really easy thing to miss. It's not like buffer overflows. We can say that if you have like a decent background in programming, you're not going to have like this, like at least the easiest one you can directly see. But the double free, it could be really hard to grasp and also really hard to find in your code. So again, if you are writing C code, don't write it with trust me, bro. Just write code with following the conventions and the standards. Okay? Learning about binary exploitation, it's not really about, it's not only about exploiting systems, it's also about writing safe code, especially in C, because you can easily mess up. So now we can talk a little bit about the early days. So C was built as a tool to abstract the machine code into the human readable code. Basically, instead of writing assembly code, you will write something which is more readable and which will do exactly what you are trying to do. And that was like the reason why C was built in the beginning. Also, C was meant to give you full control over the memory. It's not a bug that it gives you the full access. It's just how it was meant to be. And that's also one of the reasons why C is one of the fastest languages in the world. And also one of the reasons why C is still, till today, one of the most famous languages in the world. I'm talking a lot about C because I just love C. So yeah, I'm a little bit biased in this, but yeah. So C is not unsafe, but you can write unsafe code. And yeah, it really depends on how you write code. It's not like you're going to write print of hello world and you're going to tell me that you can exploit this code. If you can exploit it, then yes, C is unsafe. If you cannot exploit this, then yeah, it depends on you. You are the one who wrote this unsafe code. Does it make sense? So again, the control is like a gun. If you give a gun to a monkey, disaster is going to strike. So yeah, I think this is self-explained. Also, the first documented buffer overflow was in 1988, and it was found by Robert Tippin Morris. And just imagine, just because of this buffer overflow, the whole internet in the world, like literally the whole internet was taken down and needed a reboot to fix. Just imagine, just one buffer overflow required the whole reboot of the whole internet. Damn, yeah. Memory errors. We all hate memory errors, but if you are a binary exploiter, you love memory errors because they are your attack vector. They are basically the first entry point you have to reach a system. And yeah, so basically all attacks start by finding segfaults and abort and I don't know, any violation of the C that doesn't allow you to execute what you're trying to execute. Again, do you guys know what is a segfault? Can someone explain to me what is a segfault, please?
So as I've understood it, is like the assembly code has a register, whereas like the address of the next instruction, and if this is pointing to an area where the operating system knows there cannot be any instructions there, then it's like just giving a segfault.
Good, good. This is one of the examples of segfault, but what is it? Why it is triggered? In this example, why it was triggered? It was triggered because you are trying to access a memory. For example, you're not allowed to access, or if you're trying to jump somewhere where you cannot reach or which doesn't have anything in there. This is a violation of the execution standard that your computer understands. Segmentation fault is literally any violation of a way your CPU executes code. Literally anything this related. It can be defined in another way. Let's say your stack is not executable and you're trying to execute something on the stack. In this example, it's not going to work because you're violating something. If you are trying to access a pointer which literally doesn't exist, this is also another violation. If you're trying to read a memory which is read-only, this is another violation. Literally anything that doesn't match how C thinks of a language, not C, how your CPU thinks of a language, how your CPU executes your code, it's a violation, and thus it's is segmentation fault. One of the examples, we have smashing the stack, which is basically buffer overflow. No, smashing the stack is doing buffer overflow, but overwriting the stack canaries, and then it will be stack smash error. We also have an overwritten addresses which are in the read-only memories region. We will also take a look into what are the read-only memory regions and where can we see them and where can we find them in our binary. We will take a look into this, don't worry. Also executing code that doesn't make sense or running gadget that also doesn't make sense. Do you guys know what do we mean by executing code that doesn't make sense? What is a code that makes sense for a CPU? We are talking about machine code. So literally, any machine code that could be understood by the CPU is a valid code. Anything that cannot be understood by the CPU is also another violation and also another segfault. Okay? So any machine code that doesn't follow the standard that C understands, not C, I'm not sure why I'm saying C. CPU understands, it will be a segmentation fault. Do you guys know what is a gadget? Okay, just remember this and ask me later if I don't say it, because we will go through this later on, okay? Yeah, so, or running gadgets without preparing their place. Also jumping into addresses that do not exist, and we already talked about this, right? So yeah, the meme of this page is it's not a problem if you are awesome at it. I mean, it's not going to be a problem if you are a binary exploiter and you know how to use this. So yeah. Now we're going to take a look into the code execution. For this, we're going to be cooking. First of all, do you guys know a little bit of assembly? Who does not know assembly at all? Who thinks that he can read assembly code? Maybe not understand, just read. I'm just talking about reading. Okay, I mean, okay, so what are registers for people that can read assembly?
They are basically the only kind of memory spots that you have and you can store values in, and I think they are limited on the architecture of the CPU. I think most have 4, as far as I know.
You are talking about the hardware registers. We are talking about software registers, but it's good. It's good.
Okay.
It's good. Yeah. You are talking about the L1, L2, L3, and L4.
Exactly, this one.
Yeah. Another one? Here? Here. First row.
There are memory locations that the CPU will use to do operations.
Okay, good. Yes, that's the right answer. Do you guys know what is the difference between a register, a stack, and any other memory region, or let's say a heap? Please?
So it refers to how far they are, so to say, from the CPU itself. So the layers, you mentioned the first one, so the registers are very close to the CPU, so very close to the hardware itself, and then it goes with the layers L1, L2, L3.
What does it mean to be closer to the CPU? How is it important to us?
In the sense of access
Yes,
and control.
it will be faster.
Yeah.
The closer you are to the CPU, the faster you are to execute. That's why the registers are extremely small, but they're extremely fast. That's why they're used the majority. I mean, if you can use the registers, you should always use them because they are the fastest. Okay? Any other input? Additional input? Okay, good. What is an instruction? Come on, guys. What is an instruction?
An instruction is like a mini function the CPU can execute. Like
Yes, you can think of it that way. That's a really good abstract of it. Yeah, instruction is basically, I mean, now we can start using the board, I guess. Instruction is literally a binary or a byte code that your CPU understands, also known as machine code. Let's say the most famous one is this one, NOP. Do you guys know what is this? This is an instruction. What does it do? Please? No operation, exactly. What does it do? Yeah, exactly. It doesn't do anything. Why do we have NOP? Please, Mike.
I think it's also there to just say that the current instruction is over sometimes, or that something evaluated to false.
Yeah. That's good. That's good. It's also used for padding. It's also used to fix the stack alignment sometimes. So it has a lot of uses. That's really good. Good. Does anyone here have another input? So this instruction is basically have a number. I don't remember if it was hex 90 or 90. It's one of the two. I forgot which one of them. But this, when you write it to assembly and you compile this assembly, it will directly become this. And your CPU basically understands this. And this is an instruction. Let's say another example. We have move, I don't know, let's say 3 to RAX. What does this do? Please?
Move the value 3 into the register.
Exactly. If you really understand how this, again, this is Intel syntax. If you're using AT&T syntax, I don't know what's wrong about you. What's wrong with you then? But always use Intel syntax, okay? Basically, Intel syntax means if you're moving something, you're always moving from the right to the left. So this is going to be put here. It's literally what you're reading, the CPU going to be doing. Let's say you're trying to do something else. XOR RAX with RAX. Who doesn't know assembly here? Come on, like just now someone said he doesn't know assembly. Does anyone here not know assembly? Okay, okay, you, please. What does this do? You don't know assembly, what does this do?
I mean, XOR is the binary version, and basically we are moving what was in the racks through the...
But like right now we're not moving, because here it was written move, that's why we were moving. Right now we have XOR. What does XOR do?
all the zeros will be going once, and all the ones going zeros.
Yes, but right now we have XOR this with this. So it's literally what you are reading, it's what's going to be executed. Let's say if you have ENC, and then you have, I don't know, RDE. What does this do? Increment RDE. It's literally what you are reading going to be executed. The reason why people find it difficult, because you have to write it in a way that doesn't violate how the CPU going to execute this. This is the first thing. The second thing, debugging this is hard. If you are writing Python code and you forgot a semicolon, your interpreter or your compiler going to tell you immediately, hey, you forgot the semicolon. Assembly, it's not going to tell you anything. It's going to let you compile it. It's going to let you do whatever you want, and then you're just going to be smashed with a segmentation fault. You see where is the difficulty? But it's literally a language that executes line by line by line, and every line is exactly doing what it's saying. Okay? So it's really just about practicing like this, reading step by step. Okay, now we understand what is a stack. Who do not understand what is a stack here? No. Who do not understand what is an instruction here? Okay, good. Who do not understand what is a stack? You don't know what is a stack?
I'm not sure exactly.
Okay, can someone explain to him what is a stack? Guys, either lift your hand or don't. It's not both. Please.
So a stack is a part of memory where instructions are given. Like, for example, a function where you can redirect. We are in the main process. It is a stack main. We have a function. We move to another stack, which is the function stack, where we have instructions. Then we can go back to the main stack. That's what I think.
The instructions are not put in the stack. They are not. Also, there is a difference between, like, that's the reason why I wrote stack and stack frame. They are not the same. Stack is the memory region, which is called the stack. It's a huge memory region, which looks like a stack. That's why it's called a stack. And inside it, we have multiple stack frames. Let's say this is a stack frame. This is also another stack frame. This is also another stack frame. Do you guys know which one of these three will be executed first? Or which one of these three going to be put first in the stack? Please? He lifted his hand first.
I think always on the top it will execute it, and then it will go...
Yes. So I did draw it from top to bottom, but it's basically going to insert it here, and it's going to always grow in backward. So this is 0, then 1, then 2. Let's say if you're starting from main, basically the stack frame of main going to be here. Now, are you guys following up? Stack is basically a memory region where we have stack frames. You don't have to be confused about stack frames. We're going to explain them soon. But do you guys understand now? Stack is basically working like a stack. You are inserting the first thing, and then everything that comes afterward is going to be after it. Makes sense, right? Everyone did hear push swap. Okay, good. Now let's talk about stack frame. Who knows what is a stack frame? This is a stack. This is a stack frame. Yeah?
When you're entering a function, basically you create a new stack frame,
Yeah.
and when you leave a function, you basically pop this one stack frame.
Yeah.
So you have the state of the last function again.
Okay. What do we have inside the stack frame?
All the local variables of the function.
Good. What else? It's not only local variables. It's 3 things.
Maybe, I guess, some pointer to the last stack frame.
Exactly. That's 2. 1 left.
The size of the stack frame, maybe?
Sorry?
The size of the stack frame?
No. What? Return value is what he said. Pointer to the previous. Come on. The arguments of the function. Where are we going to put them?
I mean,
So 3 things. Return, arguments of the function, the local variable inside this function. Good? Okay, so again here we're going to the instruction. I forgot that I had already prepared slide for this stuff. Sorry guys, but let's go through this real quick. So I didn't find any representation directly between machine code and assembly language in Intel. This is AT&T. Don't write this code. Write it in Intel, okay? So basically this is a direct representation of what you see here. Move L is basically represented by B8. And this is the address we're trying to move. And this is the address. You see it? It is just on the other side because of the Indianness of the system. If you don't understand what is the Indianness, we're going to go through it later. You see? Again here, this thing is directly represented here. This is what your CPU understands fully. Like this is, your CPU understands it 1-to-1. Okay? And this is what we call binary. Like this is the real binary. And right now, if you want to represent this, you're just going to put this stuff afterwards, and this is going to make it like your whole assembly code or your whole binary that your CPU is going to execute immediately. This is literally the lowest level you can possibly reach, and the level where your CPU actually understands. Okay, make sense? Registers, these are the most famous registers that we use. We have, this is like EX. Do you guys know these registers? And what are the conventions of them? Okay, EX is meant for the return value of the functions. EBX is, wait, let's go to the ones, yeah. Okay, so registers, they have sizes. The biggest size we have is 64 bits. Here we have the biggest is like 32 bits, is because it's from 0 to 31. And they are represented by EAX. If you are talking about the whole thing, it's with R. It always starts with R. REX is just 2 AX. EAX is basically made up of AH, AL. You see what it means? And this means high and this means low. Okay, forget about the names. Just imagine every register. It doesn't matter what it's called. It has a size. Half of it, you remove the R at the beginning and you put E. Half of it, you remove the E and you just add like either an H or L. L means the lower part of it, and H means the upper part of it. This is the lower byte, and this is the upper byte. And this makes it short. Okay? It's fine. This can sound confusing, but the most important registers you have to know are stack pointers, RSP. It's the stack pointer. We have the base pointer. Sorry. We have the RBP, which is the base pointer. Guys, I was expecting you guys to know this by now. We have RDE. So these two are like related to the execution itself. So these controls this stack frame, and also where are we in the stack frame, and so on and so forth. We have RDE, we have RSE, then we have RDX, and we have RCX. Sorry, RCX. These are the arguments of the function. These are the arguments of. These are the arguments of the function. Also, we have REX. There is a convention of using these. You don't write assembly code and you put whatever you want, whatever you want. You literally have to. Do you guys know what is a convention? Yeah.
So based on what I understood so far, there are two types of registers.
Yeah.
There are default registers that we can use for operation where we
Yeah.
can store our integers or whatever.
Yeah.
And there are predefined registers
Yes.
that we can use for specific operations, like, I
Yes.
don't know, index that will point to a specific instruction or whatever.
Forget about the other type of registers. I'm not gonna give you guys here assembly. Just remember these that I wrote here. Just these. Don't think about anything else. If you have more, we have other registers. If you have more arguments for a function, we have other registers. But for now, just remember these. We have RSP, stack pointer, RBX, base pointer. We will know later what are they. We have RDE, first argument of the function, RSE, second argument, third argument, and the fourth argument. And we have RAX, it's the return value. Before you return from a function, you always put whatever you want to put here. And if you are doing like something which is external, your CPU by default gonna do it for you. So it's gonna, for example, if you are doing a syscall, this is just between brackets. I don't want to be confusing here, okay? Again, RSP, RBP are the most important too. And this, like how you build your exploit and so on, it's always thinking about these two. We also have REP. I forgot this one. This is the instruction pointer. This is which instruction you are running right now. This literally holds the instruction you are running. And the CPU always executes what is here. Okay? That's why controlling this means you have absolute control over the binary, because you can execute whatever you want. Okay? These are function arguments. This is return value. Okay? Forget about what I wrote there. Okay? Now, the stack or the stack. Yeah, so this is a stack frame. This is the whole stack, what I draw there, but my drawing is better. And this is the stack frames. So we have here stack frame. Yeah, this is a stack frame. This is also a stack frame. I will remove this later, sorry. And this is also a stack frame. You see, it always ends with the return value where it has to jump. And these functions were actually pushed there. You see what I mean? So when you finish the execution, some people think it's going to be, yeah, some people think this place is going to be destroyed or whatever. It's not destroyed. It's just going to be overwritten later on. Okay? You guys know what is overwriting, right? It's writing on top of something that is not absolute zero. It has some value, but you're going to overwrite it. So this is a stack. Now. Oh my God, okay. That was a blunder. So as you can see there, everything is jungled together. We have local variables, we have the saved RBP, we have the return address, we have like a buffer, everything is with each other. And this is going back to the architecture that we talked about, John von Neumann architecture. It has literally everything with each other. Now we're talking about the stack frame again. Local variables, return address, parameters of the function, and again, this is a stack frame of another function. Again, three things: return address, local variables, and the parameters. Your stack pointer, the base pointer always starts here, but your stack pointer always moves. Yeah?
Is it that the brackets that we write in C code kind of form these stacks behind each other?
When you call a function, your CPU creates it.
Okay.
Your CPU does this for you. You don't have to do it yourself. Even in assembly, you don't do it yourself. You just tell it what to put there.
Okay.
So you know that in assembly, you also have functions, right? Okay, now time to smash some stacks here, okay? Demo time. I'm gonna be doing the demo alone. If you guys can follow up, it's fine. If you cannot, just watch me, okay? Now, first we're gonna just try, let me show you the code that I'm trying to run. I think it was main.c. So this is the code that I'm trying to run. It doesn't have anything complicated. We just have a main, which is calling a function called printer, and then you just take the first argument we have and try to print it. This example was taken from Palm College. Even some of the slides here. Also, most of the information that I know about binary exploitation are from Palm College. It's a really beautiful platform where you can learn binary exploitation. So this is our code. And do you guys see here any bugs? there.
There's a buffer overflow in
Where?
the sprint function because you can read
Yes.
more into the
Yes,
buffer as the
yes,
buffer is
yes.
large enough, so you can overwrite the stack and can manipulate the whole memory basically.
Yeah, yeah. What else? Do you have any other input?
No, also
Okay, good, good. You have something else. Okay.
Also, the printf takes the user input as a format string, which is a vulnerability by itself.
Good, 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 good. I like it, but in this case scenario, it's not going to work because we don't have quotation. But that's a really good thinking. If you don't know what he meant by a format string vulnerability, it's fine. We are not going to cover it today. Today we just have binary exploitation and shellcode. Okay. So again, here the bug was using sprintf. Sprintf is a buggy function that you should not use. Also some other functions like gets and fgets and stuff like this. If we do, I'm not sure if it's in, if you can see it in man, but let's try. Okay, they are not explicitly writing it here. But if you are trying to compile it with GCC, no, what I'm trying to do. If you are trying to compile it with GCC, it's going to tell you there. Oh, it didn't tell you. Damn, okay. So here, this is a good example of writing good code because here the CPU didn't even find it. So interesting, right? Let's do file. Do you guys remember what does this function do, or this command, or this tool, file? Please?
So it's a command that will, so to say, MRI the file itself. So it will show details, for example, on what CPU it's running.
What do we call these? Like, where are these informations?
This,
The information that's going to be displayed now, from where are they coming?
I don't know.
It's from the header of the binary. Always remember this. The anatomy of the file, every file has a header. This is how your PC or your operating system understands that this file does this and this file is this, okay? If you run this here, so you can see informations like we said last week. This is the architecture, x86-64. This is a 64 bits LSB executable binary, and it's not stripped. Now, let's do the fun stuff. So we will fire our GDB. And now I can show you guys what I was talking about last week. So if we do info functions now, I mean, because you saw that it's not stripped, so we will be able to see the symbols. We can see the symbols. We have the printer and we have the main, right? Here's the printer, and here's the main. Now, if you want to stop in the main, which command do we have to use? Please? Breakpoints, yes. We have to break in main. So let's try to break in main. Just do an example. Here, break. Now we will run it. Run. We will run it. And yes, we did breakpoint in main. And now, can someone tell me what does this instruction do? Literally read it. Just read it. Tell me.
It subtracts 10 from RSP register.
Yes. Do you know what does this do in the background? Yes, it's subtract, but what does it mean to the system? It's basically giving you a little bit of memory on the stack. So this is giving you 16 bytes on the stack. This is what it does. So subtracting in the stack, especially when you see RSP, it means giving space. So we have at the beginning here, like this part is always called the prologue of the function. This part, it's like these two instructions are always how we start our stack frame. We always push RBP, which is going to be pushed and be pointing to the first addresses we have on the stack frame, and then we just give RBP the value of RSP, because RSP right now is actually pointing to the correct address, and RSP is always moving. So we have to save the address where our code ends. Where is this function ending? Where can we return back? This has to be changed somewhere, and this is the use case of RBP. It's the base pointer where your function actually starts and finishes. Okay, again, this part, it's always in all functions if you are trying to. I mean, right now I'm talking about x86-64. If we are running ARM binaries or any other architecture, it's going to be different. Okay? That's why I was trying with like the Docker container and so on to have an architecture that I know, and also an architecture that you guys can see everywhere. If we try to do it in ARM, yes, there's a lot of microcontrollers, there's also a lot of embedded system that uses, but I wanted to have something more generalized. Any questions? Okay, good. So again, we are stopping here, yeah?
So how is it running now for you? How have you run
I will tell you during the break, okay?
Okay.
Because it's not running internally. I'm basically I just have an SSH connection to Pound College. So that was the workaround.
Okay.
But it works, and as long as it works, don't touch it. Okay, now let's inspect some stacks. Info stack. Now, as you saw before there, 0 has the address of our main here, and has also our main. You see? So this is our stack frame. Now, let's go to the printer. We will go to the printer, and it's going to just add it there. Do you guys know which value the printer is going to have? Here? Come on, it's just going to be 1, exactly. Let's see. Break, printer. Now, continue. Okay, we are right now in printer. Let's see what happened. Did it happen or no? It didn't. What did happen? It was pushed down. Again, stack is always pushing downward. Actually, I made a mistake here. So this should be backward. Right now, if main was called first, I did oversee this. If main was called first, we'll have 0. Anything that will follow it up, it will push it down, it will be put on top. Okay? And we did see it live. We called printer, it did push main down, and it's right now on top. And that's why when we say popping, pop in what's on top of the stack. So if we pop right now the printf, it will be taken from the top of the stack. And the top of the stack should always have the highest value, which is the 0, which is the top. That's why it will be taken from there. And then main is going to become 0. Okay? Now we are in the printer, but let's go back from the start and do some other stuff. So we're going to do right now, let's see, info breakpoints. I'm going to remove them first. Yeah, del 1 and del 2. Now we don't have any breakpoints. And now we will do something else. We will do starts. Do you guys remember what does this command do? It will literally jump into the first instruction. Okay, so I have to, I will just continue till the end. Okay, so it's finished. Now I will do, yeah, I'll do start. It starts, do you guys know this start, dash start? What is this? I talked about it last time. Please?
I think in assembly it's the start label where the whole program starts.
Yes. So this is the entry point. This is exactly where everything starts. That's why if you're writing assembly code, you don't have to write main. You always have to write start. You always define your start, and your code should be under start. And in C, your CPU, when it compiles the code, it's going to add this stuff. When you have your main, it's going to add this stuff. It will add the start. It will also add the main loader, and it will also add the main afterward. Okay? And right now, if we do, for some reason, I also didn't figure out why I cannot see it in Jeff. But now, if I do info stack, I can see the start, that it's on the stack. But if I reach the main, I think it will remove it. Break main, continue. And now info stack. Yeah, you see, it did remove it, even though it should not be removed, because right now the execution is still part of the stack. So it's still part of the start. So we started from start, we loaded we called the main loader, and then the main loader called main, but still the start we cannot see it here. I don't know, maybe Jeff removes it by default. In a pwndbg, normally you see it.
Maybe just because we don't go back to like start function.
I only saw this in Jeff. I think pwndbg has it, because I'm pretty sure that I saw this before. Or maybe because of strict binaries, I don't recall. But yeah, here in the background, we have the starts in the stack frame. In the stack, I mean, it has its own stack frame. Okay, yeah?
I saw
I'm not exactly sure. I saw these endbro 60 endbro 64. Is this just like a convention where the function is starting?
Yeah. This is
Okay.
yes.
So it's not like a value that it has. It's just like assembly, or is it?
It
machine
has a
code?
value, but it's like just defines the starting point of the function in the decompilation. You see it. You don't write it yourself.
Okay.
Yeah. Okay. Now we started. Now we can start doing the fun. Okay. Now let's break again in printer. And now just remember we are. Wait. Let's go back. Let's quit, or let's just. Hello. Sorry, I didn't start my TMX session. Now we can do this, and then do break main, and then do run, and then do split terminal, and here we can see the code again. So as you can see in the code, it's actually asking for the arg1. And right now we didn't supply arg1 here. So normally it should have the null value. I will restart this, but with a good value, so that we first let's tackle having like a normal procedure, like a normal code that actually works. So I'm going back there and return. Oh, I could have just run it. Run a, but first we have to break in main. Or let's break in printer, because the most important part it's actually happening. It's actually happening in the printer. So I'm directly gonna break in the printer. And run. So if you want to give arguments in GDB, you have to give it after run. You cannot give it in the beginning. So right now I'm just giving it like 5 A's and run it. And right now we are in the printer. And if we look here again, you see that the string is actually loaded in the printer. So technically we have to see here what RDE, because it's the first, again, the first register, gonna have the first value. So it should be an RDE. Let's take a look. Let's say info register RDE. Okay, let's examine with the string register RDE. Okay, yeah, as you can see, we did examine this string. It specified that output going to be represented as a string, and we see exactly this bunch of A's here, and it's inside RDE. So it's exactly what we talked about before. RDE is the convention of having the first argument of a function in assembly. And yeah, it's exactly what we were looking for. Now let's continue forward. Who remembers what does SE do? Step in, yes. So we are going to do a step. As you can see, we are one step onward. Now we're going to jump here. Again, we're going to continue jumping because the most important part is this isPrintf. And the good thing about GDB, right now when you are trying to run like the call, it's going to tell you exactly where it's going to jump. You see, you can already see this here. You see it? Now, let's do something. I will jump from here to here. I will do it with NE. Thanks last time who told me about the NE instruction. NE instruction going to basically jump from here to here. It's not going to follow the whole instructions inside this, and it's going to jump directly here. And technically, we have to see that the pointer to the function should be in the stack. Let's take a look. NE. Telescope. Telescope basically inspects the stack. Yeah. No, wait. Before we take a look into this, because right now it was popped because we are outside of the function. You remember that we did push this into the stack, right? Now, actually, we have to find this in the stack, right? Let's see if we can find it. Examine string again. Let's see RSP. We cannot see it, but I think there is a padding. Yes, there was a padding. It was pushed in the stack, and here. We can see it here. Yeah, it's here. When we did telescope, you see it with the padding 10. You see it? I don't know why there is a padding here. I have to still take a look into this. But you see that it was pushed into the stack. Okay? Are you guys following up, or you guys are just watching me? Okay, good. Huh? Good? Okay, so now we have like a normal procedure, normal execution. We did reach that part, and normally right now we are just gonna call printf, and then we're just gonna leave. Okay. Yeah, this was like the normal procedure. Now let's smash the stack. Now let's try to do some nasty stuff. Just gonna continue. As you can see, it did print it correctly because we have everything correct. Now let's do something interesting. So we're gonna think I still have the breakpoint, right? Breakpoints, yes, still have it. I'm gonna run it with a bunch of A's. This will be definitely more than. Okay, I started without even realizing. This will be more than 16, right? So this normally should trigger the buffer overflow. Let's see if it's gonna do it. Right now, everything fine. La vie en rose, and there is no problems until we're gonna reach the place where it's gonna be interesting. So, step in, step in, step in, step in, step in, step in, step in. Now, look at here. This was what we are trying to put, right? So basically right now, we are trying to put all of this in this address, which was the address of the new here, because it's the first arguments, RDE. Again, going back to the registers, RDE has the new. This string is here. You guys can see it. Here's this is the representation, and this is where is it. And then we have the printf. Now, if you are trying to put this inside here, what's going to be? Buffer overflow. Yes, it's going to be a stack segmentation fault, but it will be the buffer overflow. Let's see if it's going to happen. I'm right now just going to continue normally. Continue. Yeah, terminated with signal, segs, and segmentation fault. Why? Because we did violate what we were asked to, and if you see it from here, yeah, cannot disassemble from PC. PC is the instruction pointer, so it couldn't understand what the hell are we trying to execute because we are trying to jump somewhere. I will tell you here what happened. Let's say this is our stack. Let's say inside it we have here a stack frame. Let's say our variables, the bunch of A's, it's literally here. Because this place of new is so small, we write, and then we reach the place where there is like the return value. Remember what I said about the base pointer? It has the value that we have to return back. Now let's imagine we did overflow this with a bunch of A's. This is still going to be for the CPU, as long as this is represented with hex, it's going to be an address. But REP, when it's going to try to jump there to execute, it's not going to find anything because literally this address is going to be 61, I think. Yeah, 61. 61, 61, 61, 61. Yeah, this is 4. Yeah, 61. And this address basically doesn't have anything. It doesn't have the code that can actually be executed. And this is a buffer overflow, and this is exactly why we have segmentation fault, because we're trying to execute in a place where we don't have anything. Yeah, please, Mike.
I mean, at the end, it's also crucial to exploit because from there on you can just call whatever you want from the PC, yes. Especially if it has administrator privileges. So
I mean, as long as you are running with, like, the process has the, like, right now, what we are talking about, why this is critical. You are executing stuff using the process itself. So if the process is allowed to do anything, you are also allowed to do it. Now, just imagine if this process had root privilege. You can literally do here wherever you want, literally wherever you want. You see how critical is this? Now, let's inspect this. Let's see what we are talking about so that you guys know that I'm not just talking crap, okay? Let's do it slowly, let's do it slowly. So, again. Yeah?
Okay, so since we couldn't fit the very parameter...
Mike.
Since we couldn't fit the parameter in the allocated memory.
Yes, it's not allocated, it's mapped.
The mapped memory, so we just we deleted what comes next as which
we didn't delete, we did overwrite.
Exactly, that's the word. we overwrite what's gonna come next, which is supposed to be the instructions, and that's what gives us a segfault.
Yes, 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 yes. So CPU basically finished the function. It's gonna try to just jump back here. It's not gonna be able to. Again, let me tell you this. It doesn't, I mean, we're gonna do it now. It doesn't segfault after. It doesn't segfault here. Again, it doesn't segfault here. It will segfault in the return value. And we will take a look into it. Running this. Now we are in main, we are in printer. So SE, 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 SE again. Now we are calling sprintf. Now, next instruction. As you can see, it worked. We did go through, like, right now, literally sprintf said, okay, you want to do your overflow? Okay, it's fine. I'm just going to do it for you. And it did it for us. And as long as this code is still executable, we can still execute it, right? Where we will have a problem. We will have a problem literally when we are trying to leave. And you will see why. SE, again. Okay, I did jump there. Fan literally goes back. Okay, so remember also this instruction. It means finish. So we did finish the function. And now we are back to the printer. And right now we are in NOP. Let me just remember the instruction, how it is exactly bytes. NOP, which is right now going to be in REP. You guys know what I'm doing here?
No.
I'm trying to, okay, so it's the next instruction. SC. Okay, never mind. I will do this later. Leave. Now one more. Wait, one more. No, wait, maybe we can see telescope already. Yeah, we can see it already. Yeah. Look at this. Look at this. You started from here, and we literally overflow everything what is afterward. So right now here it's literally garbage. So red is gonna try to read this and gonna be like, what the hell is this? Let's do it. SE. Look. Red said like, hey, I cannot disassemble from PC. I don't understand where you are trying to take me. This is something that doesn't make sense. And now it's segfaulting. You see how the segfault is actually looking like? And right now, if you take a look into the instruction, SRBP. Yeah, you see? You see what I was talking about? RBP. Look at what it did become. You see? And that was actually the overflow. So we did go through the stack frame, and we reached the return address, and we did overflow it with a bunch of A's, which is the representation in hex is 61. Okay, now we smashed the stack. I forgot what I had for. Oops, I'm in the wrong side. Okay, now we smashed the stack. I think you guys know about it now. Wait, what time is it? What time is it? 11:08. Okay. I think we have to go forward, or otherwise we're not going to have enough time. But does it make sense? Does it make sense? Okay, good. Let's go back to our slides. Now, Canary Islands. First of all, if you don't know who I come from, Morocco. I come exactly from here. And these are the Canary Islands, and this is what we use to protect against stack. I'm just kidding. But they are also called the same. They're called stack canaries, and this was just a side information. If you come to Morocco in the summer, let me know. You can be our guest. So stack canaries. Let's try to understand what are stack canaries. What are stack canaries? Oh, nice. A lot of people did. Please, yeah. It's open, I think.
Hello.
Okay.
Yeah. To prevent basically getting into the return address, you put a value before the return address, which is a canary, and it gets checked. And if it is not the value that was put in, but something else, then you just exit the program there instead of going to the return address.
Okay. Nice. Do you know what does it represent, a canary? As you can see
I don't know
here,
what it looks like.
maybe someone else, does someone here have another input? Okay, so basically, what we were talking about before, we have local variables, we have the return address. Now, this is the other stack frame of the next function. Now, as long as we know that to reach the return address, we have to go through this. Like overflowing cannot jump from here to here. It has to go through this. What they thought about was to put a random value that you are not allowed to know and you should not know about. It will be generated each time you run the binary. It's going to be a new thing. And they're going to put it here. They're going to put it before you start doing your code, and we're going to take a look into this in assembly. They're going to do it before you start running your code, and they're going to check it back before you run this thread. So before you try to run whatever is here, they're going to check if this was overwritten. You see how smart it is? So basically, they're going to put a wall here. And if you try to cross this wall, they're going to know it. They're not going to stop you. You can do this violation, but they're going to stop the program. They're going to shut down the program before you can abuse this and use this. Does that make sense? So if you find a way within the function before you reach the red, so it means before you did hit the check of the canary, you can do whatever you want. But this doesn't work because the reason why we are using this problem or this attack vector is thanks to this return instruction. That's why we can use this. You see how it was built and how the idea that came from. Okay? Now, let's go and try something. So, going back to our code, we can, oh yeah, let's, I'm right or links? Yeah, here. So now, if I do this as main, this is the code we see, right? Now, I'm back to the other side, and I'm back to the other side, and now I will try to compile with the stack protection, which is this is the flag you use to do the stack protection. So if I go back here and I do check sec, basically this command tells you which kind of protection are implemented on the binary. So we don't have canary. We have non-executable stack. We will know about this later. We don't have this fortify, and we don't have we have partial rel rule. You don't have to know what is rel rule now, but it's important for the CTF. I didn't say anything, but yeah. So you saw like these things. Now we're gonna compile a new binary, which will have this protection. Oops. Yeah, here. I'm gonna just add an output to make sure we know the difference between them. So this will be called, I don't know, canary, like this. Now we have canary, file canary. It looks the same like the other one. You cannot see here anything, but if you run checksec, canary, you can run check, by the way, you can run checksec within the GDB, and you can also run it as a command here. As you can see here, canary found. So right now we have added the canary there. Let's jump into that GDB session as well. So GDB canary. Now let's do this as main. Now take a look into this main. You see the difference? First of all, we can see that it did become bigger, right? Second of all, we can see that this part in the middle, it basically stayed the same. But there's a difference in the prologue and the epilogue of the system. Prologue and the epilogue are basically the first stuff that are executed before your code itself, and also the last things, for example, this leave and read. And now, you see leave and read. So, before this instruction, move 0 to EX. By the way, this is it's so unoptimized instruction because if you want to do this, you can just do it with XOR and EX with itself. It's just going to make it 0, and it's much smaller and much faster. We're going to know about this in the shellcode. We're going to know how to write our shellcode ourselves and how to write it as optimized as possible because sometimes we have limitations. Again, so this is the instruction, right? And if you can see what is before it, is exactly what is looking there. But we injected here 4 instructions. Here, and we are also injecting a couple of instructions here. Here, as you can see, this instruction, I mean, not all instructions stay the same because this instruction basically allocates in the stack. Right now, we don't have only for the local variables. We are also allocating for what? Canary, yes. So right now, we needed more space for the canary as well. You see how it makes sense? And these are like putting this stuff into the canary. Yeah? It's depending on, like right now, because we have a 64-bit, okay, I cannot see it anymore. If you have 64 bits, it's going to be 16. If you have 32 bits, it's going to be 8. It depends, like this 64-bit, I didn't want to dive into this, but literally every information you see with file, if it's going to work, canary, okay, it doesn't work. Let's go back, okay, file. This is in hex. 10 hex is 16. Yeah, it's not 10, it's 16. And here you can see 64 bits. That's why it was allocating 16. This 64 bits basically says how big are the chunks of the memory, or the chunks of the memory in the segments. How big are they? Also, let's take a look into one more thing. VM map. This is the thing that I want. Okay, it's on the other side. This is the thing that I wanted to show you guys last time. VM map. Because I'm making it smaller just so that you guys can see a little bit on the left. These are all the memory regions. The memory region that I was talking about last time, I mean, the thing we can use it with IDA to make our life easier was basically this address. This address. Here. This is always the start. And this is the thing you use to rebase your IDA to give you like all the addresses you need. I mean, if you have this, you don't have to walk slowly through it to make like a, I don't know, like a breakpoint here. Like right now, I cannot know this before running the program, right? Especially if it's stripped. So that's one of the reasons. Do you guys remember what I'm talking about? I'm going to show you later how to do it with IDA. Okay, now we understand what are canaries, right? We understand how they work and we understand how they can protect us. Do you guys know how, okay, wrong side again. Do you guys know, wait, what do we have here? Yeah, Q&A. Do you guys have any questions first? Yes. Yeah?
So there is always a way to know if we have a canary or not.
Yeah.
And if we are trying to make buffer overflow or exploit this vulnerability, we need to know if we have a canary or not to use it, right?
Of course, yeah.
Because we need to read it and keep it the same so that it won't be detected.
Yes. And you're wondering how to do this, right?
Yes.
So basically, this is a mitigation. Yeah, I like these questions. Basically, this is a mitigation, and now we are hackers. We have to find a way around it, right? It's always this yin and yang. So defenders are trying to add a mitigation, and we are trying to find a way around it. The way around this is basically by leaking. So this canary is basically a value, right? And now, instead of just exploiting one bug, you have to find another bug that will allow you to read addresses from the server directly. Because if I give you binary and you try to run it locally, it's not going to have the same thing that we have in the server, right? Also, even if you have like the, if you have the binary, like I don't know, if you have one of the canaries from the server, it's not going to be exactly the one which is on that runtime when we are executing that specific web server at that time, at that specific time. You get what I mean? And to do this, you have to leak. And leaking is another type of vulnerabilities. When we are going to go through the history, I'm going to show you a roadmap of Pawn, what you have to learn to become a master of Pawn, or like an expert of Pawn, or to just know what you are doing. There is a roadmap. We're going to go through it later. And it has like bugs and what you have to learn to reach like this bug to understand it. Because I can give you right now, there is an attack called JOP, basically jump-oriented programming. You might read about it, but you're not going to understand it because you don't understand what is ROP and you don't understand what is a gadget and stuff like this. There's always steps to reach that thing. And now we are basically just going through the way of attacking, like just writing something into somewhere. There is also another way of attacking, which is reading something you're not supposed to read, which is canaries. If not canaries, there's also another way. Okay? Paul, can we stream a video? Is it going to be possible? Sure. Yeah. Can you repeat it? Or should I just have it in my phone? Okay, I'm just going to have it in my computer. Yeah, it's fine, it's fine. I think everyone can hear it, right? It's already loud. Oh, I found a bug. But the poor binary exploitation guy, he's still trying to figure out how to attack it. So this is actually true. What you saw is basically the library that I'm gonna recommend you guys to learn. It's called Pound Tools, and it's amazing. It allows you to do a lot of stuff. It crafts the shellcode for you, even though I don't recommend it, at least in the beginning. You have to write your own shellcode. Also, it allows you to connect to the server directly, sends shellcode to the server, receive. It also allows you to change the Indianness of the addresses. It's really amazing. Like this Pound Tools, it's all in one library for literally everything you need in binary exploitation. Okay, we're gonna go through it later, but for now, it's a break time, and also I'm gonna give you guys a challenge, which is yeah, you will find. Okay, I have to push it. I didn't push it yet. I will push it, but can you put this image, or should I send it to you, Paul?
Just make it full screen, I can make a screenshot.
Yeah, okay. For people that are online, I didn't push the challenge yet. I'm going to push it now. Done? Okay, it's pushed technically. Yeah. I only made one challenge this week because this challenge is already hard. If you solve this, you will get a voucher. I will make the price even better. You will get a voucher of 2 months. Okay, sadly nobody was able to solve the challenge. I'm not sure if someone from the online people solved the challenge. If yes, yeah, write it in a message. If nobody wrote in the next 1 minute, then I will just show it. Nobody? Okay, then I'm just going to show the solution. We don't have enough time, so I'm just going to show you and walk you through it. But I'm going to make sure you guys understand it, so don't worry. So first, I was going to decompile it and show you guys like the decompilation directly, but we don't have enough time. So I'm going to show you directly how the code looks like. I mean, I think everyone here knows how to decompile code, right? So this is how the code looks like. We have a vulnerable function, which has a buffer 128, and then we are just reading 256, which is already representing a buffer overflow vulnerability because you're trying to read more than you can take. And they always say, never try to eat more than what your stomach can hold. And that's so true. So this is the code. I think everyone figured out that we have here a vulnerability inside the buffer. And our task is basically to return from here, redirect it to here, right? I think everyone did figure out that much, right? But now, how can we do this? I'm going to show you directly the solution, but I'm going to walk you through it, and we're going to do it together. First of all, this is the name of the library that I was talking about. It was called, it's called pound tools, and you always do from pound import all, or just do like import pound. And basically, this pound library allows you to do a lot of stuff. First thing, I always like to do this because it saves me a lot of time, especially when you are writing shellcode yourself. Context arch EMD64. This thing defines which architecture you are writing code for. By default, pound tools writes for architecture x86. x86 and x86-64 are not the same. EMD64 is the same as x86-64, not x86. Does it make sense? Okay, these are two different things. Good. Next, second thing is Linux. Indianness, you can also define it here as little Indian. And do you guys notice the Indianness of a file? Yes. Please, someone? Yeah? Mike, please. Here.
It's the order in which the individual bytes are stored. So the most significant to be first is big endian, and the least significant to be first is little endian.
Yes, and we're going to go back here to show you something. Look at this, guys. Look. As you can see here, this byte is literally being put here. This is little endian because you are putting the little bytes first. And this is how we are doing stuff normally. I mean, when you are trying to send stuff over the network, it's going to become big endian because if you are trying to send packets, we always want to know how big is this packet before we send it. If you're trying to read it from the least significant bits, you're not going to know immediately how many bytes you're going to be sending. But if you read it from the other way around, you're going to know how huge the thing you are trying to send. This is just brackets, okay? Now going back to our code. Context terminal, only psychopaths like to have tmux splitting horizontally, because if it's horizontal, you're not going to see the registers, you're not going to see shit. I will show you how it looks like without this, and let me show you immediately. So I'm going to remove this line, okay? I'm just going to comment it out. I'm just going to comment it, and I'm going to try to run my solve script. So let me just go back, and I'm going to run my solve script. So you can see it did split vertically. Now, just like right now, just to see like what do the register have, you have to do Control-B, do the square brackets, and go slowly like this just to see it, then do escape, and then go back. Why? Like, serious, why? You can just do, wait, let me quit this, and you can literally just do this and just split it like a normal human being, like this. Now, you can literally see everything you want to see. You see this, you see the registers, you see everything. Okay, so that was this on the side. Yeah, context terminal, you define basically how GDB is going to be run. Then you define like the binary path. And these two addresses are really important. That's why I said you guys have to get this stuff dynamically. Don't try to calculate it yourself, because most of the time it's going to be wrong. So what do we need to know? Like, what is the difference between them? We always have to know where is the buffer address and where is the vulnerable return address. Isn't it what we are looking for? The address where our buffer starts, and basically the return address. Just subtract the two, and it's going to directly give you the addresses, the buffer size. And if you are asking me from where did I take this, well, there is a lot of ways to get this. There is some tools called, like, for example, NM, even though NM, no, forget it. If you want to do this, the easy and straightforward way, just do it through GDB. Now, if we open GDB and we go to reach that, to reach like the function vuln, we're going to do it now. You're going to see that this address is exactly the address where the vulnerable buffer starts. And this address, no, this is the return address, sorry, the vulnerable return address. And this is exactly where the buffer size starts. If you don't trust me, you can do it. You will find these two addresses, and here, look, my buffer, I mean, my payload is basically A just multiplied by this. And I'm printing it here just so that you guys can see it. Now, second thing. Now we also have to know where is the win function. One of the ways to get the win functions is to get it from the binary. So you're going to go through the debugger, but for example, through info functions, or any way to get like for where does this win function starts, right? Forget about this SM red queue. Forget about this. Just imagine this doesn't exist, like this part. Just think about this part, okay? Now, see how Pound tools is really amazing. You don't have to look for this address yourself. You can just like binary, which like where the binary existing with this elf constructor, and then just gonna look through the symbols because the symbols are all existing there. We're not stripping binaries. Just look for win. And this return of this is gonna be exactly where the address of it. You see how amazing this Pound tools is? So Pound tools is a tool to help you be more efficient in your stuff. I mean, all of this, you can do it yourself. You can do it, I mean, manually, just through GDB. And it's good to do it once or twice or 3 times. You are still learning stuff. It's good. It's fine. But later on, if you're trying to be fast, if you're trying to make good improvements in binary exploitation, you should always know how to use stuff to its maximum. You know, you should use it in a way it helps you achieve more. Okay? Now, okay, let's say you forgot about this. Now, this Pound tools gives you 2 ways of running a binary. You can either create a process. We can do it now. It's not going to start GDB. It's just going to run it directly for us. Just going to do this. Just going to do boom, go back here, and then quit this from here. And then just do pound so. Yeah, it worked anyways. So you see, when I just run the process, it will just run it directly, like purely without opening the GDB instance. But this is not good if we are trying to debug and test stuff. So always, when you are still testing your exploit, you're still experimenting, always use this debug, GDB debug. This always starts your instance for you. And what I define the context for the terminal, it's what's actually being run here. So here, you basically start the terminal, and also, and one more side note, this has to have, you have to have a tmux to run this. Do you know what is tmux? It's basically a terminal. Yeah. You have to have tmux to run this. With GNU terminals, it's not going to work. Okay? I mean, it might work if this terminal that you have allows splitting of the screen. It has an embedded tiling manager inside. Otherwise, it's not going to work. Does what I said so far make sense? Does anyone here have a question about anything that I said so far? What, please? Mike?
What is the elf doing there? The
Good question. Okay, our binary, when we did like file command, it tells us that this binary type is elf. We can take a look again. Let's take a look again. So, I mean, I have right now a shell in the system, so I can use file already here, and they do A outs, for example. You see this? This is the type of the file. This is the Linux executable type, which always runs on Linux. If you have Mac, it's Mac O. If you have Windows, it's portable executables, which is a PE. Okay? Any other questions? Okay. Now we're going to go through the payload. So you guys now understand what we had as a prerequisites before. Now we can start actually crafting our stuff. First thing is the offset, like how much do we have to go through to reach exactly where the return address is, which is what we did calculate here. I mean, if I get rid of this and I put the value which I received like from this print, it will work fine. It's not going to be any problem in this. But always try to do stuff dynamically, because later on, when we are going to learn about a mitigation called pi, this pi means that every time you run a binary, it will have different addresses. In this case scenario, it's not going to work. Okay? I mean, it's still going to work here if you take them at the same time. Like in one run, you take them at the same time because the offset is not going to change, right? But if you're trying to do more complicated stuff, for example, the win address is going to be different. Okay? So here, always try to do stuff dynamically. Now, if I try to run without this, and I'm going to do it now. I'm going to try to run it without this rate queue, and you will understand where it's going to be problematic. So I'm going to get rid of this. Yeah, just have to get rid of this. And also, one side note, this command do, process P is what we started here, process read until this. So if you go back to the child one, you see that I had here this thing here, and that command, this command, yeah. So this command, read until, means we're going to keep reading from the standard input until we reach this part. The moment we reach this part, we're going to write this payload. Why I used to write and I didn't use send line, because there is another command or another function called send line. Send line always have \n at the end. Sometimes you don't want this. You want to have exactly what you send, exactly working there. That's why you use write. And P interactive means let me interact with the server. That's it. Now let's try to run it without this thing. We are racing against the clock. You see how binary exploitation is complicated. It just needs time. What I was gonna do? I forgot. Oh yeah. Yeah, we have to start GDB instance, or else we're not gonna see what is the problem. Now, if we try to run the solve script again, and we continue, and I try to switch to the other side, because you can already see that it's segfaulting. Look, segfault. Now if I jump there, it's not going to give me anything, even though it looks almost the same. It looks identical to what we were. It looks identical. You see, it doesn't give me anything. Now, look, listen. Look, now if we do info registers and we check RSP, look what you're going to see. You see this 8? It means that the stack, where is it right now? It's not in a nibble, which has a 16 in it. It doesn't have a byte, which is a multiplication of 16. Now, let's add the rescue, and then we will see how it's going to see now. How it's going to look like. Adding this again. Run it again. Continue. It worked already. But if we stop it and we do inspect, or no, that's inspect. Right now it's running already in, no, my bad. So we have to actually breakpoint in the win, otherwise we're not going to see it. Let me run it again. You understand what I meant? Like right now our shell is already working, so we are in a new process. But I want to see it within the win. So I'm going to break in the win like this. And you see like this address here. It's exactly the address that I took directly using symbols from Pound Tools. You remember? Yeah. Now, let's continue. And we did hit the win. Now, if we do info, registers, and we do RSP, look at this. Look at this. You see? Now it's aligned. Now we are able to execute our system. I was going to display more how the attack goes, but I would leave this to you guys. I think right now you guys understand it a little bit. From where to get the addresses, like what you have to calculate, and because we have to go through the shellcode and we don't have enough time. So always look for the address of the buffer and then the return address, just subtract them, and then you will get your offsets. And then if you get the same problem that I had right now, if you think your script is actually working but you're still getting segfault, always remember that we have stack alignments. It's always something that you have to pay attention to. Okay, good? Any other questions? Yeah, please.
We had all the problem that we couldn't run it. Did you compile it in a weird way?
No.
Because it was like showing some dependency issue or something. We could not even run the binary.
I had to add a loader or something before it.
Yeah.
Okay.
So we all
Okay, my
we all
bad.
spent the time trying to run it and then couldn't even.
You
do
could
it.
have told me at the beginning. I could have fixed it because it was working for me on the server. That's why I assumed it's working. My bad. Sorry. But next time, please let me know before the time of the.
Maybe it was like part of the challenge. That's why we were like,
No,
what's going on here?
I'm not that evil. No. But okay, thanks for the info. Next time, I will try to play test it out before we start doing stuff. Okay, now let's go back to our slides. Now what if when doesn't exist? What are we gonna do? When doesn't exist? Fine, I will do it myself. What are you gonna do if when doesn't exist? Give me ideas. You don't have to know the answer, just give me ideas. Come on guys, ideas please. Just throw something, you're not gonna lose anything.
Modify memory on the run ourselves manually.
Okay, but you want to execute something. What are you gonna execute?
Yeah, okay.
Look for weaknesses like gets or.
Let's say
printf
there
and
is
stuff.
no, like, we have a buffer overflow, but we don't know what we're going to do with it. We don't have system. What are we going to do?
It's always smart to have a shell on the host.
Yeah, but let's say binary doesn't have a shell, doesn't have system, doesn't have anything. Please, there.
Try to get access to memory and write your own code into memory and try to execute this.
Exactly. This is what we call about shell code. Shell code means a code that's going to give you a shell. I mean, if there is no shell in the server, we just have to create our own, right? And now, let's say our stack is executable. If the stack is executable, it means it can execute instructions that are already on the stack. And this is from where the idea came from. So shell coding means, I don't know why this image does not show up. Anyways, I even forget what this image represents. Anyways, so shell code is basically compiled code, machine code, which is ready to one-shot your system. It's ready put there directly system. It runs on the stack. It's built by overwriting the already existing values on the stack. I mean, same idea of overflowing. And so lange Rede, kurzer Sinn, or long story short, it is running compiled assembly code in the stack. Why shellcode? Also, this slide is taken from Pound College. I mean, there's a lot of slides taken from Pound College here because I just think they are amazing. Usually the goal of shellcode is to get like a shell. That's why it's called shellcode. And this is a representation of a shellcode that gives you a shell. It's written in assembly. You basically just compile it to a raw. You turn it into bytes that I talked about before, and you just put them in the stack. And the stack will just execute them because it's executable. If the stack is executable, sorry. Does it make sense? Anyways, the slides, they're going to provide it later. You can take a look how it's already built. This is just the system call for execve. And okay. Now let's talk about some issues. Now let's say, for example, your shellcode has 0, null byte. If you are trying to call this function will require this byte. Sometimes you cannot have this because remember again the stack, it has a metadata which is the 0. You are not allowed to have zeros on the stack. You understand, like, right now, where the problem can arise. You're trying to make your shellcode, but your shellcode will not be running because your bytes that you have there have something that would trigger something else. And here are like basically some problematic methods and like the bytes that are actually problematic inside. There is always a way around, and basically just change a little bit your instructions. So instead of moving 0 to rex, first, this is huge. Like this is the representation of this instruction in binary. You can do it with just XOR rex and rex. If you XOR any two things together, it's just going to give you 0. Because their bytes going to be matching, and then it's just going to be canceling each other's. And this thing, look at how small it is. And it doesn't contain zeros. You see? This is just one example. These are other examples that allow you to like either make like your shellcode shorter or allows you to bypass like these restrictions that I talked about before. Feel free to look at these again, especially if you are going to do the shell injection module in Pound College. You will need to know this stuff. Yeah, demo time. I was going to show you guys here how to. I will show you. I will show you just real quick. So basically, yeah, let me close this. Yeah. Again, I'm using Pound tools again here. Look, if you want to do it like the manual way, I will also show you the manual way, which is like writing proper assembly code and then the makefile that will compile it. But if you want to do it with Pound tools, which is the most efficient way, you just define your code under assembly, and you're going to define your context here, and the Pound going to do it for you. The Pound tools library going to do it for you. And if you want to debug it to understand where the problem is, if it doesn't work, you can just call this function. GDB debug shellcode, just give it a shellcode, interactive. It's going to work like a charm. I always use this to make my own shellcodes. Again, I will provide the, I can also send this exploit later on. I mean, this exploit is basically modifying the, it's a running chmod, you know guys, change mod of a file, which is here, the flag, to be like to be readable by me. So that's what I'm doing here. Now going back here, okay, demo time. What do we have else? Oh, sorry. Demo time. Yeah, now let's say that you cannot execute. Let's say your stack does not allow you to execute. For example, here, NX is enabled. You cannot do this stuff. So what are we going to do? Does anyone have any ideas? Okay, let's see. The idea is roping. Roping is a method called, or stands for return-oriented programming. It basically allows you to use gadgets. What are gadgets? Gadgets are basically instructions that already exist in the code that do a specific thing. You can chain them together to achieve something else. Why this thing works, as simple as I can say it, is because your stack, if it's not executing stuff, it allows you to jump. So the return that I talked about, even if the stack is not executable, it will always return, right? Now let's imagine the return address gonna become this. Gonna jump here, do something, return, then again, jump here, return, then again, jump here, return. You see? And then you can jump again somewhere and redo stuff. You see what I mean? You can put this stuff on the stack and it will work like a charm. Also, you can also make, you can also call system with bin bash, also with roping. It only needs to put 3 things on the stack. You pop RDE. Popping RDE means pop the last value on the stack and put it in RDE. This is what's the meaning of pop RDE. You pop RDE, as I said, it's going to pop the biggest value on the stack. Let's say this is our stack. You're going to have here pop RDE and then ret. This pop RDE and ret. Under it, you're going to have the bin bash. Why under it? Can someone tell me why under it? Because you are popping from the stack, so it's going to take the biggest value, the last value on top. So pop RDE, it's going to take this, put it into RDE, like this. Now, if you're trying to run ret, as long as this is popped, this is going to be squeezed again. Under it, we should only have system. So this is going to be returned, which means we're going to continue. and this will have the address of system. And now system, when it's called, RDE has already the bin bash, which means system gonna run with bin bash. And you have your shell. Isn't it amazing? But for this to work, you should have the system somewhere. You should know the address. This is Ropin. And you can make even more amazing stuff. There is, in any binary, almost any binary, there is a gadget, one gadget, literally one, that does everything. That does execve, pops a shell, and does everything for you. Ropin is my favorite. It's my favorite topic. Yeah. Q&A. I guess you guys have a lot of questions related to this topic, but yeah, sorry, there is no enough time. But if you have any questions, you know my intro name, you can always DM me. Okay? This is for next week, before we talk a little bit about history, because I have history there. Bring your own laptop. Next week, we're going to have cryptography. We will dive into the good crypto stuff. It's not going to be the boring math stuff. I mean, we're going to have a little bit of math, but it's not going to be super math intensive. Just for me, please try to look into RSA, especially RSA. Just know how it works, because we need to go a little bit faster. You see, you don't have enough time to squeeze everything into hours. Try to take a look into RSA. There is Computer Phil. This YouTube channel has 2 videos. One is explaining RSA from a non-mathematical perspective, and there's another video in the mathematical perspective. Watch them both. That's all what I'm asking for. Come here understanding what RSA means and what RSA does. That's it. And other than that, just have some rest. You don't have to do a lot this weekend. I don't want you guys to burn out. And just come next week and we will have a lot of fun together. Also, next week prize is going to be different. If you solve the challenge, you're going to play 1 CTF with my team. Yeah. That's a lot of, that should be a big prize. So make sure you prepare RSA. So a little bit of history. It's going to be super fast. Sorry. First bug, we talked about code injection. The first buffer overflow that turned down the internet. The second vulnerability recorded was a stack smash. All the vulnerabilities here are red, and all the mitigations are green, and they are in order. So this is a stack smash. Then we have non-executable stack to basically shut down what we had before. We had then like a red to libc. As long as you cannot execute on the stack, you can also go back to libc, because as long as you are loading dynamically libc, you have access to all the addresses. Only if you know the first address. If you know the base address of libc, again, base address is when you do VM map and you see the first address. That's the base address. It's the address that allows you to calculate. You don't have to know that address especially, but you have to know an address in the libft so that you can calculate. Because offsets are always the same. You only have to leak one of them. Afterward, you have snack canaries. We talked about them, the Canary Islands. Then we have heap overflow. Yes, you can do buffer overflows also on the heap. It also works, but you have to be super careful because we have a lot of metadata in your chunks when you are allocating the memory. We have heap mitigations. There is a lot of heap mitigations. I cannot talk about them all here. Format string. It's basically when you run printf without specifying the format and then the variable. Like when you do quotation, %s, and then you give the variable, this doesn't have any bug. If you do printf and then give it directly the string, it will run. It will work. But this is a format string vulnerability. Okay? Because it will allow you to both leak stuff and also write stuff. Because there is an interesting thing that you guys, I think nobody here knows about it. There is %n. %n in printf allows you to write into the memory. Yes. Yes. That's, yes. Just look at it through the manual. Read the manual. RFTM. We have format guard. We have a lot of them. ASLR. It's basically the randomization of the kernel. So basically, the kernel is going to have randomized memory each time you run the binary. And we have here like first bugs of info leak. So basically, you're using format string to leak a memory and then use it somewhere else. You see, like right now, we are starting to make a combination of reading, like leaking, and then using this leak of to do like some more advanced stuff. Okay. Then we have info guard, which is like also some mechanisms. Then we have instruction set random, blah, blah, blah. Here where is ROP, first ROP even recorded. It's in 2007. You see it's almost 20 years between like the first ever buffer overflow. No, it's 30 years. Yeah, 30 years between the first ever buffer overflow and the first ROP. And we have also JOP, which are similar, but you're using jumps. There's SROP, which are system roping. We have BOP. I don't know what is this. I cannot tell you anything for sure. We have also GIT ROP. GIT is just in-time compiler. It's mostly, this is for browser attacks. And there you go. Now we have even more stuff, blah, 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 blah. You can take a look into this later. These are the most advanced stuff, okay? And there is no way you're going to jump and understand something from here without understanding what we had before. There's also a roadmap. You guys are literally still here. There is like all this stuff here that you have to understand first. There is also integer overflow. This is another topic. There's format string, which has like either leaking memory or writing to memory. There is also the global FSAT table. Another hint for the CTF, understand what is this. Because you will need to understand this to solve one of the challenges, okay? Understand this, global offset table, what it's used for and what is the mitigation and how can we attack it. It's also bypassing ISLR, which is basically leaking memory. And these are heap exploitation. Heap exploitation, you're not going to see it in the CTF because it's super complicated and there's absolutely no way someone with no prior knowledge will be able to solve the challenge in this. So I'm not going to do it. So you can forget about this, but look into this, a little bit of this, a little bit of this. Try to look as much as you can. Yeah, again, practice, practice, practice. If you don't, I know every single one of you here, and they will watch you. And I think, yeah, that's it. Thank you so much for your time and your attention. See you next week.